So the meeting will now, the presentation by Miguel Prado and Edson Signor. And they will tell us about these systems with leakage. Okay, so quantum and classical version. Go on.
Hi, good morning, everyone. Okay, we are going to present our project about other kind of open system, specifically the system with Hall or leaking system. We are going to apply with the standard map. This project is with Edson, Professor Lea, and the Professor Sandra Prado in Brazil. Okay, the motivation where there exists a numerous physical situation in which a hole or a leak is introduced in another wise closed system. Well, not necessarily the system is closed, but we are focusing this. For example, the natural origin of the hole, because the system has a hole like in aerodynamics system, and because it can make the measurement device, you have the closed system, and when you have measurement, this interaction, you can see like a hole, because you can also be used to reveal the dynamical properties of the closed system.
Okay, so you studying that because it could be a real hole, so that's why you're calling natural origin. It could be a measurement that you can see as a whole, I understand. And also you put that because that will help you understand better about the closed system.
Exactly. Yes, in different areas and application is from acoustic, billiards, chemical reactions, hydrodynamical flow, planetary science, optical microcavities, and plasma physics. Yes. Okay, first we start with the difference between this open system. For one part, we have the leaking system, and the other is the system. You can open the system with the interaction with environments. The difference is in our case with leaking system is you have the trajectories escape or they are removed of the system. If the closed system is conservative, then when you have the hole, the system become conservative after. Conservative system remain conservative after become leaky. And the persistent chaos or the asymptotic dynamics becomes transient chaos.
Okay, and can you tell us what you mean by conservative remaining conservative?
Well, conservative means that the phase space don't have contraction in the dynamics, the volume of the phase space. And if the system is chaotic, the conservative system means that the sum of the Lyapunov exponent is equal to 0.
Very good. Jonathan has, sorry, Jorge. Jonathan has
yes, please, let me ask you a question, Miguel and Edson. Is about these terms of persistent chaos and transient chaos is relative to time or to space? I mean, persistent chaos is just chaos forever, and transient chaos is chaos only for a certain time scale, something like that.
Yes, exactly, because yeah, for example, in the persistent chaos, you can define an asymptotic Lyapunov exponent for maybe an attractor or the complete phase space. But in the transient chaos, you have a temporal time in the system is chaos, and after maybe the system have other level of case or the system becomes regular. In this means is transient chaos because there exists a temporal scale.
Okay, but for this case, the system should be time dependent. I mean, if you have the system described by Hamiltonian, which is time dependent, or this can happen also for time independent Hamiltonian, like conservative systems.
Yes, for both case is general. Yes, you can
Okay.
have transincase in dissipative system independent of time, or you can have something chaos in time depends Hamiltonian.
They will show to us the system.
Yeah,
John.
okay, okay,
And
thank you.
understand what they have, right? I see in the phase space, there is a hole. So you have the object moving and choom, it disappears.
Yeah, but so
Go on, Jorge.
Okay.
Speak louder so.
yeah,
so they can.
is in relation in this part is my question. So you preserve the size of the phase space always.
Exactly.
And
This is an
the
important.
meaning of the conservation.
Yes,
Conservative.
exactly.
Oh, yeah. But
Yes.
this is not in association with the conservative number of particles, for example. This sort
Yeah.
of thing.
Yeah, you don't
Because if you lost the particles.
Yes, exactly.
Yeah,
You
exactly.
lost
Mhm.
exactly.
Okay.
Good point.
Yes. Yes, in this sense, you lost material.
Information.
Information. No, because energy is yes, particle. You lost particle. Different to the interaction with the environment.
Right, and now you're going to
yes.
explain the interaction with the environment, right?
Exactly. And that's then the difference with the when you open the system with interacting with the environment, the properties that you exchange energy, matter or information with the environment. You have an additional phase space, and you are interacting between the system and the environment. In this, the system, the phase space of the system is contracting, and the dynamic of the environment can influence the system. And in general, then you have a system, the environment, box with their Hilbert space, and you have an additional terms that how how is the interaction between them. Yeah. Then the phase space, the total phase space or total Hilbert space in the quantum is the product tensor. And here the total Hilbert space is
It's
just
just the system.
the system.
Mhm.
Okay, how do you resolve for the classical methods for both systems? For example, when you have interaction with the environment, you can resolve the problem with differential equations. For example, you have aquí the oscillator, the fourth driven oscillations. Then if your system is closed, you have oscillations. But if the system is interacting with the environment, with maybe friction, then you have
Losses, no? So
Yeah.
you will.
Then you have the damp oscillator, no? I
Right.
mean,
yes, exactly.
not the force, okay.
Other methods is with Fokker-Plan equation or Langevin equation. You can obtain the dynamics for this kind of equations. For the leaking system, you can analyze the trajectories in the phase space. Then the initial position of the particles or the trajectories and how evolve in the phase space. And you can analyze the properties of the trajectories during between the escape. And you have Sabine's law when the hole is very small.
This drawing is it correct? The one on the right? Can I show to you?
Yes.
So like you started here?
Yes.
Why didn't escape when you
Ah,
crossed?
yes, sorry, yes. Yes, because this system is a billiard, right? The cardio billiard.
Yeah, cardiac.
You have a hole,
Mhm.
then you have, this is the real trajectory, but you can have the dynamics with other coordinates, with the angles and the momentum, and you have transformed the real dynamics in a map. Then this is the phase space of these coordinates. Then you have a map.
Okay.
Yeah.
So I can, like in the drawing, I can see here it's escaped here where the hole is. And then
Exactly.
you map this into this
Mhm.
plot.
Or-
Okay,
exactly,
okay,
exactly.
fine. So that's why, then I cannot just, I don't know,
No, it's not the same trajectory.
it's not the same.
Yeah,
trajectory.
because
Yeah.
the position actually is just the angle when you hit the wall. This is the
Mm.
definition for this position. And the momentum, I think, is the momentum right after that comes out this.
Yeah.
This,
It's a
that hit.
conservative system in the moment.
Yes, it is,
exactly.
it is. Mhm.
Exactly. Exactly, the connector before and after the collision with the barrier of the villa.
So both systems are different, yeah? A and B are.
No, it's
No,
the
no,
same.
it's the same.
system.
It is
Yeah.
just, you're just mapping the billiard
Is
in a different way.
Yes.
It is kind of Poincare sections.
Um,
You're doing, but the Poincare section here is like every time you hit the wall in the billiard.
Mm.
So which angle that you hit the wall, it is basically your x-axis in the map, and the momentum, it is the momentum that you hit the wall.
Okay, I think I got it.
So you're transforming the billiard,
yes. In a map.
into a map
Mm.
to analyze it.
Then what is the gap in the second picture?
Hmm.
The gap in the second picture, it is exactly basically the occurrence of this slits, right? The slits, the leak. The leak.
Yes,
He's asking, no, this.
yeah, this is the hole because you
Mhm.
have the billiard, then you have a hole in the barrier, and this is the angle, right? You can map this angular coordinate with the angular in the barrier of the billiard.
Yeah,
Mhm.
so
That you are
that's
open.
That
Oh.
S is not the position, is the angle.
Exactly, it's the
Then
angle in
when
the
they
barrier.
hit the wall, you see that the segment changes direction.
Exactly.
Well,
Exactly. And this if you any particular of any momentum go out of the system, and for that reason here
Yeah,
is
so it's not really what is happening physically. The left one is
Yeah.
what you would see. The right one is a map.
yes,
Okay.
exactly.
Okay.
Yeah.
Let me see now, the left one, sorry, left one is the configuration space.
The left one is the real thing.
Yes, exactly.
This is the phase space or the configuration space?
The right is the phase space.
Yeah, and the left is the configuration space or the real space.
Ah, yes, exactly.
Yeah.
Yes.
Okay.
Yeah, yes. Thank you. Well, this is for the classical methods, but for the quantum methods, then for when you have interaction environments, when in general you have this form of the Hamiltonian,
Mhm.
the total Hamiltonian is equal to the Hamiltonian of the system, the Hamiltonian of the environment, plus the interaction.
Right.
And this interaction is described, have the coordinates of the both.
Mhm.
And there exists a lot of methods. One of them is you can construct the master equation for the density matrix. We have the differential equation with the trace, the environment, trazando el
Trace
entorno.
out. Uh-huh.
Yes, and you can obtain a master equation. One example of master equation is the Lindblad master equation. Other is the Caldera-Leggett master equation, the optical master equation, Markovian master equation. But this is important because this has all the requirements for a physical density matrix.
And that's what the Vesh told us. right?
Yes, it is the exact. Other method is you can add a complex term to simulate the dissipation in the system, and do you have a effective not Hermitian Hamiltonian, and you can solve with maybe Eigenvalue problems and study the system. For the other system, you can for leaking system, then you can construct a dynamic operator, and this operator is another Hermitian operator. Then you can analyze the spectrum of this new operator that include the projection with the whole. Yes, and this is the talk of
That's
Edson.
Edson will tell us, okay, so
Yes.
and everything will be based on the evolution operator, the propagator.
Exactly.
Okay.
Yes, okay. Just for example, for our system is the standard map in the current regime, and this is there exists experiment with this system, and is very good for like a tool system. Also, they have all the dynamics of chaos systems. Then we can use to research.
So this is the one that Edson told us, right?
Yeah, exactly. That is just quick. We remember that the system have a nonlinear parameter, and the dynamics depend of the value of this parameter. Here is regular. This is a mixed system. This is strongly chaotic. Then we are going to focus in this strongly chaotic.
Okay, okay.
Okay, and then we analyze the open system. This is just classical. Then for interesting thing is this is, if you observe, the phase space is totally chaotic. But if you calculate the finite time Lyapunov exponent, you can observe a structure in the phase space.
Okay, so here is the finite time Lyapunov exponent. Mhm.
Exactly. Then you can observe a linear structure
Mhm.
in the strongly chaotic regime. And we are going to study the difference if we have the whole. In this part, we have small values of finite time Lyapunov exponent, or if we put the whole when the finite time Lyapunov exponent have large values.
Very good. So let me just repeat that.
Sorry.
So the blue ones are the low values, right?
Yes.
The blue ones are the low values of Lyapunov, and the yellow ones are large values of Lyapunov. So they are going to put this whole on top of the blue to see what happens, and then on top of the red. So that's what we are seeing in these two figures, yeah? The top and the bottom. Okay. Good.
Exactly. And we open the system, and the result is that
Mhm.
this we observe in color the initial condition that escape in one time, in one interaction, two interaction, and three interactions. The same in this. We can observe that the structure is a little different.
Miguel, so
Yes.
each color tells us about if it's one iteration is the blue,
Yes,
and then
Green.
green is two, and
Red.
then red is three. Okay.
Yes, exactly.
I have a question.
Yes,
So this is the color is the Lyapunov, the finite time Lyapunov exponent.
On the
exactly.
left.
For each point, yes.
And how do you select the finite time in
Mhm.
the
Okay. Very good. Good question. When you open the system, you have a time of escape for each initial condition. Then for each initial condition, you calculate the finite time Lyapunov exponent of time escape of that initial condition.
yeah.
Yes, and then yeah.
Nice.
Yeah. And
But sorry,
Yes,
is this
yes.
a kind of average in the phase space? Because
yes,
if you
exactly.
start in different positions in the phase space,
Yes,
maybe the particle has different time to escape.
yes,
It's a kind
different
of
cap.
average.
Each point has the
Proper time.
proper time.
So he
Proper
used
escape time.
this time, right?
Exactly.
For each part.
Exactly.
For
Each particle,
Each-
exactly.
each
For
initial
each
I'm
particle.
thinking that any point in the phase space has the same finite time, but
No, no,
any
no.
time,
Each one has,
oh,
yes.
yeah,
Yeah, yes, exactly. Yeah, it's a lot of initial condition, and for each initial condition, you calculate the finite time Lyapunov
At
exponent.
the time that the particle escapes.
Yes, exactly. Along the,
Yeah, you can see the map, the different colors. Like for example, the colors in the red colors, they're the same trajectories that escape in the same time. For the blue one, it
exactly.
is just like, I think it's the blue, it is just
Yeah.
one interaction.
Yes, exactly. Then
Okay.
for this
So then
initial
you can see-
condition, you calculate the finite time Lyapunov exponent for one time.
Yeah,
Mm.
I see.
Yeah, and we calculate the time, average time for each case. And we observe that when you put the hold when the Lyapunov exponent have bigger,
Large
large
values.
values, the time is
It's
is
greater.
is greater than the case when you have the hold in the small value of the finite time Lyapunov exponent.
How do we see this by looking at the top and the bottom? Because now we have what more green? Green was the two iteration.
No, green is a one iteration. This is the same. Maybe it's the same initial condition.
How do I see that in the bottom panel, the trajectories are staying longer? Isn't it through the green? There is more green. Green was two iteration. There is
Green,
much
yes,
more-
too.
Because now I see much more green in the bottom.
Yes,
No?
maybe.
Mm.
Maybe you can. There exists a measurement, the entropy, entropy of sets, of partitions. Then, if you observe the phase space, you can split the phase space in conjunct of how is the time of scale.
But Miguel, look, in the top, there is a number 5.1. In the bottom,
Yes.
there is a number 6. So
Yes.
this number is telling me that it's taking longer for the particles to
Yes,
disappear.
the average, yes.
Okay, so this is the average of all these colors that you have here,
No, for all the particles.
right?
Yes.
So that is already telling us it's longer
Yeah.
and probably became 6 because, okay.
Okay, I have
Yeah.
a question, so in relation with this comment, right? So I'm thinking that or expecting that the plot is symmetric, is a kind of signature of symmetric in the system, because if you move, for example, the
Yes.
gray rectangle in the same place, but in the other side,
Yes.
could be the same, yeah? By symmetry.
No. Yes, exactly. For this case, if you put the hole here, yes, it's symmetric. Yes, of course. Yeah.
Okay, so sorry,
No,
so
no.
the time I see 5.1 top 6, so it's taking much longer for this scale.
Yes.
And how about the right?
And the right is the average of the finite time Lyapunov exponent. Then
It became smaller.
smaller,
Very
exactly.
good. And it's good.
Well, we is above the classical system, and we observe that the average time at the average of finite Lyapunov exponent depend where you put the hole, and the structure is very important, and can you help to control this quantity? Now, Edson present the quantum.
What they want.
Okay. Can you guys hear me?
Yeah.
Yes?
Well, I
Yeah.
can. I don't-
Yes, they can. Okay, perfect. So, just to comment here, sorry. It is interesting that we can see these kind of structures. I will show at the end the influence of these structures in the quantum system. So that's why it is important just to see the classical one, because once you reach the quantum system, actually you're going to see the influence of these structures. They are called stickiness. Then, and you can change the slit, as Miguel said, and see how they influence the system. Okay, but let me go for the quantum map. Okay, here's just a review about the closed system. So if you don't remember my presentation some weeks ago, so what is the quantum map for the closed system? It is basically we associate the states with this operator called the evolution operator. So I have a state in a time, let's say n, and then this operator will transport my state for a time n+1 for the next period. It is the same thing that the classical system it is doing, the map is doing, since I have some position and momentum at one time, and then the map will interact the position momentum for the next period. Okay. Just remember that since our classical phase space it is toroidal, so I will have discrete momentum n position. So then what is the result? It is this finite Hilbert space. And I could relate with the H bar, this finite Hilbert space. And once I'm saying semi-classical limit, basically the H bar tends to 0 is saying that my Hilbert space, it is getting bigger, it is growing. One important property of this toroidal phase space for the quantum system, we have these phases that they come up because of the topology, but here, so because the operator would be way simpler if these conditions are periodic, so we just put it alpha and beta equals to 0, so the system preserve parity and time reversal symmetry. Okay. Right. For the Kicker rotor, we have this Hamiltonian, and we could write, okay, how this operator looks like for this specific system. We have the operator here. Here's just a review, but if you have any questions, just ask. And we could write this operator in position representation. So then once you have this operator, it is a matrix. So you can diagonalize this matrix and study the eigenvalues, which they are this complex form called eigenangles or quasi-energies, and the eigenstates are called the Flucade states because they are conserving periods. Okay, but this is just the closed system. This is just a review. But about the open quantum map, or the quantum map with leakage in this specific case. So to open the system, as Miguel said, we construct this in a certain way. So basically we have our same U operator for the closed system, but we also multiply by this other operator called the projector. And this projector basically projects on the complement of the whole. So basically what I'm saying that the system would be the same in the phase space where the whole doesn't exist. So basically in the normal, this white part. But once I reach this whole, then my particle completely disappear. So it is basically this explanation of this introduction of this operator here, the projector. In this specific case, so this is not trivial calculation, but for our case, we select this leakage as a strip of some width. Here I put a more generally delta, and this strip is parallel to the momental axis. So it doesn't matter which momentum I have in my particle. If it reaches the hole in that position, it escapes the system, it disappears. Okay. I could specify that some other momentums, then it is so the velocity so high that it doesn't escape, but this will brings more complications to how this projector is. Okay. So just to see how this matrix looks like, I'm doing the same thing, projecting the position representation, putting this operator in the position representation. And how do I find these zeros? I can expand this element of matrix. I just put the identity for the momentum here. And you can see that in this part that whatever momentum I have, if my position belongs to the strip, this term is going to be 0. So then for any values of m here, this whole term is going to be 0. So basically, let's say that this element here, n, when n belongs to the strip, I'll have 0. So you see that it will be the columns of my matrix is going to be 0.
And how many columns will depend on the width of your.
Exactly. So I just, if I put a very long width of my strip, then I have much columns, like just going to be 0 in my matrix.
Very nice.
And the other part is just the closed system, because we are projecting just in the complement of the whole. This is the action of this projector.
Okay.
And what is this? Well, and this is convenient because actually this projector in position representation for this specific case of the parallel momentum axis, it is a diagonal matrix. So that's why we could do that. So basically, when your position belongs to the strip, it's going to be 0. Then you're going to form these columns, and it would be 1 otherwise, because then you have your own matrix from the closed system.
Okay.
If you choose, for example, let's say that the whole it is here in the middle, not for all momentum, then this projector will be way different. And yeah. But this is the usual way that people work with, because it is simpler. Okay, any questions about it?
No, very good.
Yes, I have a question. So sorry. I didn't understand your explanation about of this last equation, because I can see that you have this bracket PM with QN, and you
Okay.
have that. My question is, what happened with this? I believe it that PM and QN are orthogonal, or not, or no.
Yeah, here you have
Because, okay.
yeah, here for the bracket we have usually we have the Fourier relation between them. But since
No, okay.
yeah, because I can transform from position to momentum.
Okay.
And when the position it doesn't belong to the strip, then they have this normal Fourier transform. So that's why the system it is the same. The operator is the same. But
No,
for
okay.
our case, we are saying that okay, but once the position is exactly in the hole, then it doesn't matter the momentum, this is 0. It is just a easier way.
Okay. Yes, I can understand you. Thank you so much.
No problem. Okay. So we can study the eigenvalue problem since let me go back here. Since we just have the operator in position representation, right? We can study the eigenvalue problem of this case. And just to compare, so remember for the closed quantum map, this operator U was a unitary matrix. So the eigenvalues was this form, the complex exponential, and we have this what is called the eigenangles. They are from 0 to 2 pi, and we have the eigenstates at Floquet states. I said this before. But now, since we open the system, this new operator U tilde, it is a non-unitary matrix. Basically, like when I have Hermitian Hamiltonian for a closed system and a non-Hermitian Hamiltonian for an open system. Previously, I had a unitary matrix, and now I have a non-unitary matrix. So the eigenvalues for this non-unitary matrix is not simple, like just for this complex exponential with this theta real, right, from 0 to 2 pi. Actually, we have a complex phase. So this theta is now a complex number. So this is the eigenvalue problem for this case, when I'm saying that my eigenvalues are this zk, and the format of this z, it is, we still have, I'm preserved the name just because this is a real number. So we still have the complex part, but now we have this decreasing exponential, because say in the more general case, since this can be a complex number, then I times I would be minus, right? So I have this second term, a decreasing exponential. And this gamma here, gives me the decay rate of each state.
Very good. And this factor of 2 is to get, once you put 1 there, you have the half.
Yes, because because when I put like z square for the probability, then it's gonna be just
I see. Then
e
you
to the
just have
minus
e
a
minus
yeah.
gamma.
That's why this 2 here. So this is the decay rate for each state, or you can say that the inverse of the decay rate, it is the dwell time of this state. And now we don't call the eigenstates as fluid states because we don't have conservation here. So they are called resonance. And this name comes from scattering theory. That's why they are called resonance. Okay, so people has been studying this kind of system a lot. And one property of these eigenvalues, as I said, since they have this format, if I plot in the complex plane, remember that before, since I have just the complex exponential, they are all in the edges of the unitary circle in the complex plane. But now I have this decreasing, the exponential decreasing in my term. So then they are inside this circle right now. And we can name different kinds of resonance of this eigenstate of these states basically.
So, Edson,
Mhm.
what is the y-axis and the x-axis? Or it doesn't
Oh, it
matter?
is the complex plane for the energy.
So the y is
for
the
my-
imaginary part and the
Exactly.
x is the real.
Mhm. So before, when I have this format for my closed system, they are all in the edges of the circular unitary. But now, since I have this decreasing term, they actually are inside this circle. And I can associate, for example, if my system has a high decay rate, so low dwell time, basically escape very rapidly, we call short-lived resonance. They are very close to the orange because the decrease.
gamma is very large.
Exactly. And we can have long-lived resonance because the decay rate, it is very low, or the dwell time is very high in this sense. So they will be closer to this radius 1, to the radius 1 of this in this circle. Okay?
Very good. So, okay. Yeah, good.
Mhm.
And the radius is 1 because it's, I theta is 1.
Exactly.
Mhm.
So for chaotic systems specifically, people has been studying this, and there is a very characteristic distribution for these gammas, for the decay rate. So if you plot the distribution of the decay rates of this resonance, actually you're gonna find that for low resonance, you have this super sharp resonance that they call, and you're gonna reach a peak. And this peak, I think, was Shapeliansky that showed that it is corresponding to the classical decay rate. So you can use some classical measurements to find what is I think it's the average decay rate, right, for the system. And then the maximum of this distribution, it is associated with this classical.
This is very interesting.
Mhm.
Okay, so let me just understand.
Mhm.
So the first points that you have are the super short-lived, yeah? Is
Yes.
this right? Okay. And then you reach a peak, and this peak has this classical connection.
Yeah, this is just numerically solve some problems, you know, just
It's just numerical, I
yeah.
see.
Mhm.
Sorry, I have the question. In the classical decay is, well, I don't know, is when people introduce the dissipation in the velocity. The
No,
system?
no, just the with
Yeah,
the time.
the same system, just
the
the
same
leaky system. The same that
It's without modification in the.
no,
It's
it
the
is the
same.
same one, so you can
No, it's the
compare
same, yeah.
exactly. So
Yeah,
if
that's
if you change the system, then it's gonna change the decay rate.
Okay, yeah.
So it must be the same.
Very nice. Edson.
Okay, so this is just a typical characteristic that you can see when you plot the distribution of gammas for chaotic systems. If you do this for other regime, mixed or integrable, it's going to be totally different. Actually, I propose this problem because it's not difficult to do that, just to see how this distributions looks like.
So, okay, so this distribution will be completely different if you have an open regular system.
Yes, yes.
Exactly,
it's-
because you have some stable islands then,
Right,
and then these stable islands, they can, I
so
mean,
you can have a longer tail.
exactly, it is very difficult, so they can hit the hole. Sometimes they never hit the hole. So
And this connection that you said, the peak is connected with the classical decay, what you're saying is there is no theory to prove that, it's a
Not yet.
numerical.
exactly.
More or less.
More,
More or less because for this case, the system is strongly chaotic regime.
Uh-huh.
And for this, the
Mm.
survival probability of the particle is exponential.
Decay is
the-
exponential.
Then
Uh-huh.
this peak is related with the average of the exponential
Decay.
distribution, yes,
yeah, but
In the classical case.
in the classical
Uh-huh.
case.
I don't remember if he proves that this is always going to be true.
No, but maybe it's connected with the exponential value.
Okay, yeah, sure. Okay.
Very nice.
All right. So people actually also try to understand the gaps of this resonance. They try to find a lot of properties. So this is a very active area. But I would like to concern about the resonance, about the eigenstates, the eigenvectors for this operator. So since we have this matrix, the U tilde, which is a non-unitary matrix, what is different here is that our left and eigenvectors are different. So usually when you are working with some unitary matrix or Hermitian Hamiltonian, your right and left are equal. So when you do the bracket, you have a Kronecker delta. But now, actually, you don't have this property anymore. So the right eigenvector is different from the left eigenvector.
And how do you find the right and the left? Because you have the U and you're going to diagonalize, right?
Yeah.
So then the columns will be your vectors.
Yeah, here you can use the Hermitian.
And then you use
Yeah,
the
the dagger.
Hermitian of the U
Mhm.
to get to the
Mhm,
left.
exactly.
Okay.
So you can use the dagger. Just be careful that you're gonna have the complex number here.
The complex
Yeah.
of the system.
So if you want the correct eigenvalues, but then you can find the left ones. Of course, we have some trivial eigenvectors since remember I have just columns of zeros. So then I will have some eigenvalues which is going to be 0 for this one, and my eigenvector will be 0, 0, 1 for this specific position and 0, 0 otherwise. So this are the trivial eigenvectors for the right, and for the left is going to be like just the row instead of the column. So they are not interested in this sense. And one important property here for just chaotic regime, it is that the eigenvectors with smaller gamma, which I'm saying that with the eigenvectors, the states that survives longer in the system, they are concentrate on the forward trap set. And what this forward trap set means, it is basically the trajectories that never hit the hole when I iterated forward in the classical system. So I take some initial conditions and iterate them forward, and then I see that they never hit the hole. So this set of these trajectories are called the forward trapped set. And I could do the same thing backward, right? Have a positional momentum and iterate backward and see if it hits the hole, and do the same set for the backward, and they are connected to the left eigenvectors.
And evolve backward just means change the time and put
Yeah.
minus t.
But okay. So just to see how these eigenvectors look like, I'm gonna apply them into a Husimi distribution. For this specific case of the standard map. So that's why I'm saying that for liquid quantum standard map, because I'm gonna apply them for this specific system. Just to remember how we do Husimi distribution. So once you have a state, you use the coherent states of these systems and you project your states in these coherent states, which is the states with minimal uncertainty that you can have. And basically what you're gonna have, it is this quantum phase space of your state. Okay, so this is just an example for the closed system. I presented this before. So we can compare some classical structures with the Husimi distributions, right? For different values of chaotic parameter for K, for example. But now I'm gonna do this for the resonance, for the open case. So what you can see that we can see a lot of plots here. So basically what I'm doing, this is the right eigenvector.
See, because it's all black.
Yeah.
Go on, you will guide us.
Yeah, actually, this is a good example because once I do a Schur decomposition, you can see better
Much
the
better
yeah.
than this. Okay, good.
So this is the right eigenvectors and this is the left eigenvectors. So the Husimi distribution of them. And I ordered them in with respect to the gamma. So here it has the lowest the lowest decay rate and here the highest decay rate. So this is basically just escape with one interaction if you're saying
We
for
don't
the
see anything. That's the one on the right is really black.
yeah, because it basically represents the column. Remember that I said for the trivial eigenvalue, which is 0, I have the eigenvector just 0, 0, 1, 0, 0, 0. And then if I do the Husimi distribution, just a line.
And there is a thin green dash line, and that's to tell us where the hole is, right?
Exactly. So here this dashed line, this green dashed line, it is where I put the hole in this case. And here in the corner are the classical plots. So this is iterated forward and this is iterated backward.
Okay, so if I look at the classical plot on the left and I see the first one on the right case quantum, they look very similar, no?
Yes, and we could see that because it has the lowest decay rate. So it is the state that persists more in the system. But we could not see for the other cases. For example, for this one, for this decay rate, we barely see anything. And this is difficult because since my right and left eigenstates are different, they end up overlapping with each other. So I don't have a consistent phase space representation for this.
And can I ask you, what is the classical one on the top right?
This one, it is the classical map iterated backward.
Ah, so that's what I was going to
Yeah.
ask, because it looks like the
Exactly.
left.
So that's just to like prove, quote unquote, prove my statement here, right? That the eigenvectors are concentrated in the forward trap set. So basically we can try to see the forward system to the right eigenvectors and the backward system to the left
So
eigenvector.
at least for these ones with the small gammas, there we can see a quantum classical correspondence.
Yes.
Yeah?
But if you're trying to study, for example, someone that we call fast routes that escape very fast, actually don't have much information about it because of this non-orthogonality for these eigenvectors. So yeah.
So I think there is a stronger similarity between the first picture of the right
Right.
to the classical one.
Yeah.
But for the first picture of the lab to that one, I don't see a very strong similarity. Like
There is like it's hard to see because
Yeah,
it's
I
very
think
black.
it's hard to see.
You see those things that look like these things.
Like ellipses.
oh
Yeah,
yeah.
It shows up there also. It's
yeah,
hard
because
to
you can
but it's
see the
hard.
black ones.
I have a question. So the left vectors and the right vectors are not orthogonal if you preserve the same index, or yes?
No.
Yeah,
No.
yeah, if the left and the right are orthogonal between
With the same
them,
index. Yeah?
but left between left, no.
No, exactly.
Yes.
Yes.
I
Okay,
see.
yeah. Mhm.
Left and right, yes.
Mhm.
But can you repeat
Yeah.
this louder so we can record that?
So basically what he's saying that if I do the left and the right, it will be orthogonal, but right with the right is not going to be orthogonal. Mhm.
Yeah.
Okay.
Yeah.
Mhm.
thank you.
Yeah.
Just to verify something that there is
Mhm,
also
mhm.
in the calculation.
But so we don't have a base from a proper base from our eigenstates. That's important part. So what you can do actually, we can do what is called a Schur decomposition to get a proper base for this problem. So what is this Schur decomposition? So for any matrix, you can have this you can do this unitary transformation. So basically you transform your matrix in this way when you have this upper triangular matrix, this T matrix, and your eigenvalues are in the diagonal of this upper triangular matrix. And you're gonna have this unitary matrix Q when it is composed by these vectors, V1, V2, and Vn, and they are orthogonal to each other. So you can use these vectors as your base.
Okay, Edson, just a moment. So let me go back to the T then. Diagonal are the eigenvalues, which are these complex numbers. And what is T1, 2, T1, N?
It is
T2N?
the elements that you can find doing this transformation. I will talk
You will
how
explain.
yeah,
Okay.
how you do it.
Just one more, you
Mhm.
keep going. But the Q, to choose the Q, I can pick any basis that I want. in the
Yeah,
first one.
actually, we're gonna use this non-orthogonal set to construct this Q. So so the important part here is actually to obtain this information about the Q matrix, right? About this orthonormal basis. To find these vectors that they compose
Okay,
a
so we are
orthogonal.
going to see how you're going to build that, and I see the Schmidt. Okay. go
Yeah.
on.
So basically, how do you use that? You take your non-orthogonal set and use a Gram-Schmidt process. It is the same process of diagonalization, the KR algorithm. Okay. So how this entails, basically, you choose first one state. So we choose this first one, this first state here, and then for the second one, you ensure that it is orthogonal to this first. So
Okay, so this P1 is one of the eigenstates of the U tilde.
yes, exactly.
Uh-huh.
On my eigenstates.
And right, right? or
Right.
left?
Yeah. But
That
I can
doesn't
do
matter.
with
Okay,
the
because you're
left
going to
house. Yeah.
Create them,
Mhm.
you force them to be orthogonal. Okay, and then you go, so this is going to be the V1.
And then I constructed the second one. I ensure that it is orthogonal to the first one, and then do the third, and ensure that it is orthogonal to the second and the first. And then I construct my whole vectors from this.
Okay, so now
From
we
this
have
analysis.
the V1, V2, Vn.
Yes, from this Gram-Schmidt process.
Right.
But you see that I can choose, I mean, this is the choice of this state is arbitrary.
Right.
I can choose what is the first, what is the second, what is the last one, arbitrary. So since I have capital N different states, I can have a n factorial different sets for my Schur decomposition.
But does it matter? Which one?
It matters because basically what is my first states that I'm choosing. So basically let's say that the right selection for this case, it is to choose for the first one, the state that we have more information. So basically this state here with the slowest decay rate.
So you look for the smallest gamma and then you select that state.
Yes, this state is going to be my base to start with. And then I say, okay, what is the second state that I can use it? It is the second smallest
So you
gamma.
keep this order for
Yeah,
the
I have first to
frequencies
order the
also. Okay,
gammas
so you-
because the last one, it is the one that I have any information about the systems, so I don't have any information. So that's why I order first and then construct my base with this order.
Okay, so this is very good. Isaias, this is going to be important for you, okay, if we try to do that. So it's all based on the ordering of the gammas. Okay.
Yeah, one thing that you can see that basically my first state, it is similar to so this first state doesn't change for my Schur representation because it is the first one, the base that I'm using.
And because also in this base, they have more information about the phase space than the resonance.
Yeah, basically we are
Because it's so
No,
slow, you
exactly.
Yeah,
get more
you
information.
will
about
have
the
more
phase
information
space.
about your system, about the phase
More
space.
information and orthogonal now.
I see.
Yeah, and you have to use the second, you have to choose the second one, and then for the second one, you choose the second lowest
Yeah, you go gamma 1, gamma 2,
Exactly.
gamma
Mhm.
3, and psi 1, phi 2, phi 1.
So that's why I'm ordered first and then do the calculation for
Right.
the Schur
Then you go
decomposition.
with Gram-Schmidt.
And then I have a vector corresponding to this eigenvalue. So instead of using the resonance, the eigenvectors of my U tilde, I use the Schur vectors corresponding to this eigenvector.
Very nice.
Okay, so I do the Husimi now for these Schur vectors and how they look like. The first one, actually, we can see any difference because it is the same eigenvector.
Right,
So,
exactly.
but for the second, the third, and let's say for this very large value for the gamma, actually we have some information about the system.
Yeah.
Then we can compare, try to find, okay, what is the trajectory that correspond to this eigenstate here. Same for the left. If I do the Schur decomposition for the left, I can have more information because I'm sure that they are orthogonal to each other. They are not overlapping, so mixing information between each other.
Very nice. Very nice.
Here I have a better picture that you can understand.
Yeah.
This is just for the right, okay? So here for this case, I have my hole just in this position here, point
Around
0.2. Yeah.
Mhm.
So you can see that for this for this high value of decay rate or low dwell time, they are basically concentrate in these red parts, which is fast routes, right? Decay escape very fast. But you see for this low decay rate, right? So for slow routes, I can check that it is in this white part. So basically not color, right?
Okay, so C and D have a different value of gamma, yeah?
Yeah, they have. So this is representing a slow route, and this is representing a fast route.
Okay.
And I can check with the classical system. And I can do the same thing if I change the position of my slit, of my hole.
Very nice, huh?
So you can
the
see here is
match.
in the green, for example, but here for slow decay rate, I can now see slow routes, which is the white part. And I can just see this because of the Schur decomposition. For this part, I could see it just with the resonance without the Schur because they have more information about the system, but the fast routes I cannot see it. Just with the Schur decomposition. Okay, so one thing that we can calculate now, since we have this proper base, it is the entropy of these Husimis, right?
Right.
So if I'm calculating entropy of the Husimi, we have the definition of this Wehrl entropy, which is called a quasi-entropy because Husimi, it is a probability distribution, it's not a probability distribution. For our case, since instead of this integral, right, in phase space, since we have the quantum maps, our Q and P are discrete. So I just have to sum, I just calculate the value of the Husimi, log the Husimi, and do the summation. And we included this normalization because I can say that if my entropy it is 0, then I have a fully localized state. So basically a point in my in the Husimi, and if my entropy it is 1, means that my state is fully delocalized. So covers all the phase space equally. Okay, and the normalization for this case, it is just 2 log m, and m is the size of the Husimi. Okay, this is just no.
Very, very nice.
And then what I can associate is basically if my state it is spread, I have a large entropy, and if my state is localized, I can have a small entropy.
Bye.
Okay. So here was just to exemplify one of the calculation that we do in our work is basically we put the holes in different positions. And then, as Miguel said before, that we have this structure called stickiness that basically changes the hyperbolicity of the system. And then we can check the quantum influence of these structures. So for example, once I put the slit here in the middle, I preserve these structures. And then I expect a localization in my quantum system. So once I have structures in the classical system and I'm going to the semi-classical regime, I expect a localization in these structures, due to these structures in my quantum system.
And
And we-
that's why you get a smaller value for the end.
Yeah, so on average, our entropy would be smaller, right? We
Mhm.
expect a smaller entropy because we have more localization. And compare with a slit that covers this structure, so we are not preserving the stickiness, and then we see that the entropy it is higher in the same. So we could
Very,
localize the influence of these structures.
Uh-huh.
And here it is just like I start to vary the slit for many different slits in this map. So from 0 to 1, and see how the entropy change on average. So you see that near these structures, the entropy is higher because I'm basically killing them,
killing them.
and then it is lower when I preserve them.
Wonderful.
And then just some problems that I propose for this case. So the first one is just to set the operator, just the matrix. So you just have to calculate the closed one, and then just put 0 in the columns that we want, where it's going to be the slit. So I propose a slit here, and just to construct the evolution operator.
So this is a problem for us to do the evolution operator with
Yeah.
that slit between 0.2 and 0.4.
Yes.
Yeah? Okay.
The second one is just try to do the distribution for the decay rates, because once you have the operator, just diagonalize
Right.
and just take the eigenvalues, and from the eigenvalues the decay rate. So
Mhm.
take these decay rates to make the distribution. And the third one, I propose to change the k, because I just put a k equals 10, which is we have strong chaos, and now for 2, for example, we have a mixed system, and you're going to see that the distribution is very different, because we're going to have some stable islands and other structures in the classical system. And then check that the right and left eigenvectors are different. This is just not orthogonal. Yeah. So I don't know if you have any other questions.
Excellent, very good. I'm going to stop recording.
Mhm.